Long before history named it, before chronicles whispered of the Black Death, something ancient was already moving through the veins of the world. Around 1200 BCE, as Bronze Age cities traded grain, livestock, and ambition, an invisible organism was quietly adapting. It did not march with armies. It traveled in fur, in fleas, in the dark corners of granaries and ship hulls. Its name today is Yersinia pestis, but in its early form, it had no name, only consequences. This was not yet the medieval pandemic that would later devastate continents. These were earlier strains, evolutionary experiments, circulating among wild rodents, livestock, and human settlements. Ancient DNA recovered from Bronze Age skeletons suggests that this bacterium was already present, already learning how to survive in both animals and people. It may not have caused the explosive pandemics of later centuries, but it may have shaped communities in quieter, more subtle ways. In a world where grain storage attracted rodents and trade routes connected distant ports, humans and animals lived in biological proximity. Every shipment of wheat, every herd driven across a valley, every ship leaving harbor carried more than goods. It carried ecosystems, and within those ecosystems, pathogens evolved. The story of plague is not only a human story, it is a story of animals, microbes, and the fragile architecture of early civilization. History remembers kings, wars, and collapsing empires. But beneath those visible dramas, another force was at work, microscopic, adaptive, indifferent. If the Bronze Age collapse reshaped the ancient world, we must ask, could disease have been one of its silent architects? To understand the great pandemics of history, we must travel back to their forgotten beginnings, to a time when plague was not yet legend, but possibility. The year is around 1200 BCE. Across the eastern Mediterranean and western Asia, cities rise from stone and ambition. Fortified walls guard storehouses filled with grain. Bronze tools flash in the sun. Trade caravans move between kingdoms, and ships heavy with cargo cut through coastal waters. Humanity is scaling up, building larger settlements, storing more food, domesticating more animals. Civilization is accelerating, and in that acceleration, something else is growing, something invisible. Grain storage attracts rodents. Rodents carry fleas. Fleas carry bacteria. In the ecological shadow of prosperity, a microscopic organism begins refining its survival strategy. Today, we know it as Yersinia pestis. But in the Bronze Age, it had no name, no diagnosis, no theory of infection. It existed only as fever, swelling, confusion, and death, misunderstood, unexplained, attributed to gods or fate. Imagine a child in a thriving port city. One evening, he develops a fever. His lymph nodes swell painfully beneath his arms. Within days, his condition worsens. No one understands why. In a nearby valley, a farmer watches several animals in his herd collapse without warning. In the harbor, rumors spread of sudden deaths among dockworkers. These events feel isolated, random, unconnected. But what if they are not? History would later remember the Black Death of the 14th century as one of humanity's greatest catastrophes. But genetic research over the last decade suggests something unsettling. Early forms of this bacterium were already circulating more than 1,000 years before the medieval pandemics. Ancient DNA recovered from Bronze Age human remains indicates that Yersinia pestis was present, evolving, adapting, experimenting within animal and human hosts. These early strains may not yet have mastered the explosive flea-borne transmission of later centuries, but they were learning. At the same time, the Bronze Age world was approaching collapse. Major civilizations, from the Hittites to the Mycenaeans, would fragment within decades. Drought, invasions, political instability. These explanations dominate the historical record. Yet disease often hides behind more visible crises. So we must ask a bold but careful question. What if plague, in an earlier, quieter form, was already shaping demographic shifts, weakening communities, and amplifying instability? Not as a dramatic single apocalypse, but as a slow biological pressure. If the Black Death was not a beginning, but a culmination, if it was the mature expression of an ancient evolutionary process, then the Tiao story of plague does not start in medieval Europe. It begins here, in the Bronze Age, in granaries, in rodent burrows, in trade ships, in the fragile interface between humans and animals. The threat did not arrive with spectacle. It arrived quietly, and it may have been rewriting history long before history learned its name. To understand the collapse of populations, we must first understand the organism. Yersinia pestis is a gram-negative bacterium, meaning its cell wall has a thin peptidoglycan layer and an outer membrane that protects it from many immune defenses. Under a microscope, it looks unremarkable, a tiny rod-shaped cell. No dramatic features. And yet this microscopic structure carries molecular tools capable of overwhelming the human immune system with astonishing speed. Its lethality lies in strategy. Once inside a host, it can disable immune signaling, multiply within lymph nodes, and spread into the bloodstream. In its bubonic form, it causes the infamous swollen lymph nodes, buboes, that defined later pandemics. In its septicemic form, it floods the bloodstream, triggering shock and tissue death. In its pneumonic form, it infects the lungs and spreads directly through respiratory droplets, making human-to-human transmission brutally efficient. 3 clinical expressions. 1 evolutionary genius of survival. But this deadly bacterium did not begin as a global killer. Its ancestor, Yersinia pseudotuberculosis, still exists today and typically causes a relatively mild intestinal infection. It spreads through contaminated food or water. No dramatic pandemics. No continent-wide collapse. At some point in evolutionary history, however, genetic mutations, including the acquisition of specific plasmids, small rings of DNA carrying virulence genes, transformed a gut pathogen into a systemic invader. This was not a sudden leap. It was incremental adaptation under ecological pressure. One of the most critical evolutionary steps was adaptation to flea transmission. Modern plague relies heavily on fleas as vectors, organisms that carry pathogens between hosts. In later strains, the bacterium can form a biofilm inside the flea's digestive tract, blocking it. The starving flea then bites repeatedly, regurgitating bacteria into new hosts. It is a grim biological efficiency. Yet genetic analysis of Bronze Age strains suggests something fascinating. Early forms of Yersinia pestis may have lacked the full flea blockage mechanism. If that is true, then early plague may have spread differently, perhaps less explosively, but more persistently. Instead of sudden pandemic waves, we might imagine recurring regional outbreaks, lower transmission efficiency, but longer presence within communities. A slow burn infection moving between animals and humans, embedded in daily life. Not an obvious apocalypse, but a biological undertone reshaping demographics over generations. Ancient DNA recovered from Bronze Age skeletons in Europe and Central Asia confirms the bacterium's presence thousands of years before the medieval Black Death. Yet the genetic signatures differ. The absence of certain virulence factors suggests an evolutionary stage still in progress. This changes our perspective entirely. The plague was not a medieval anomaly. It was an evolving ecological force, experimenting, adapting, refining itself within the interconnected world of humans and animals, long before history recorded its name. To understand early plague, we must step away from the human-centered lens. Civilization likes to imagine itself at the center of history, but microbes do not recognize empires. They recognize ecosystems. And in the Bronze Age, The most important ecosystem was not the palace or the battlefield. It was the space where animals, grain, insects, and humans overlapped. Wild rodent populations had existed for millions of years before cities. Steppe marmots, field mice, rats, these animals formed stable ecological networks across Eurasia. Within these networks, bacteria like Yersinia pestis could circulate quietly, causing limited outbreaks but rarely threatening large-scale collapse. The system was balanced. Predators controlled rodent numbers. Human density was low. Contact was limited. Then agriculture changed everything. Grain storage created dense, artificial food sources. Storage pits and granaries became rodent magnets, stable, warm, protected environments with unlimited calories. Human settlements unintentionally engineered ideal breeding grounds for both rodents and fleas. What had once been a dispersed wildlife pathogen now found itself living at the center of human infrastructure. Civilization did not just build walls. It built habitats for disease. At the same time, domestication intensified proximity. Goats, sheep, cattle, and horses were no longer distant resources. They lived beside homes, within city boundaries, inside enclosed compounds. Animals concentrated parasites. Parasites carried bacteria, and every new layer of density increased transmission potential. The domestication revolution was a triumph of productivity, but biologically, it was also an experiment in microbial opportunity. This is where zoonotic spillover enters the story. A zoonosis is a disease that jumps from animals to humans. Most of the major infectious diseases in human history began this way. Early forms of plague likely circulated primarily among animal populations, occasionally spilling over into humans. The signs may have been subtle. Unexplained livestock deaths, clusters of fever in small communities, infections that did not yet explode into pandemics but lingered. Imagine a shepherd noticing that several goats die within days. No visible wounds, no predators, just sudden weakness. Weeks later, members of his household develop high fevers. There is no germ theory, no microbial explanation, only fear and interpretation. In such a world, animal death and human illness blur together into mystery. Yet biologically, the connection may have been precise. When we shift perspective away from kings and wars and toward rodents, fleas and livestock, history begins to look different. Population decline may not always follow invasion. Economic stress may not always begin with drought. Sometimes it begins with ecological imbalance. The death of animals may be the earliest signal, the quiet warning that a pathogen is expanding its reach. And in that sense, the fate of humanity may have been foreshadowed not in royal courts, but in barns and burrows. Around 1200 BCE, something extraordinary happened. Across the eastern Mediterranean, multiple complex civilizations declined within a remarkably short span of time. The great Hittite Empire fractured. Mycenaean palace centers burned. Cities across the Levant were abandoned or destroyed. The intricate trade web that connected Anatolia, Egypt, Cyprus, and the Aegean began to unravel. Historians call this period the Bronze Age collapse, a systemic breakdown of interconnected societies. The dominant explanations are familiar. Paleoclimate data points to prolonged drought in parts of the eastern Mediterranean. Archaeological evidence suggests invasions or migrations, often associated with the so-called sea, peoples, political instability, overextended trade networks, and economic fragility likely amplified the crisis. These factors are real and supported by substantial research. Civilizations are complex systems, and when enough stress accumulates, they can fracture. Yet there is a variable that often hides behind more visible disasters: disease. Epidemics rarely leave clear archaeological signatures. A burned city is visible. A drought leaves environmental traces. But a pathogen moving through bodies may leave only subtle demographic shifts. Trade networks, the very arteries of Bronze Age prosperity, also function as biological highways. Ships carry grain. Grain attracts rodents. Rodents carry fleas. Fleas carry bacteria, such as Yersinia pestis. In a tightly connected trade system, infection can travel faster than armies. Port cities deserve particular attention. They were dense, mobile, and constantly exposed to foreign goods and foreign ecosystems. Sailors, dock workers, merchants, livestock, grain shipments, all concentrated in limited space. Such environments are ideal for zoonotic transmission. If early forms of plague were circulating in animal reservoirs, port hubs could have acted as amplification points, not necessarily triggering a single dramatic pandemic, but generating recurring regional outbreaks that weakened populations over time. It is crucial to be precise here. There is no definitive proof that plague caused the Bronze Age collapse. The current evidence supports drought, migration, and political upheaval as primary drivers. However, emerging ancient DNA research shows that plague bacteria were present in Eurasia centuries before the medieval Black Death. That opens the door to an epidemiological possibility: disease as a contributing stressor within an already fragile system. Not the sole cause, not a dramatic headline event, but a biological pressure amplifying existing instability. When complex societies collapse, it is rarely because of one cause. It is convergence. Climate stress reduces harvests. Political conflict disrupts trade. Migration increases movement of people and animals. Disease exploits density. Each factor reinforces the others. If early plague strains were circulating during this turbulent century, they may have operated quietly within this convergence, invisible in the historical record, yet biologically consequential. The Bronze Age collapse may ultimately remain a multi-causal mystery. But once we include microbes in the equation, the narrative deepens. Civilizations do not fall only to swords and droughts. They can also erode from within, cell by cell, host by host. And if plague was present in the shadows of 1200 BCE, then the collapse of empires may not only be a story of geopolitics, but of ecology. When we imagine plague, we often picture the explosive pandemics of the medieval world: sudden death, mass graves, cities overwhelmed. But early forms of Yersinia pestis may have behaved differently. In the human body, the infection likely began the same way: fever rising without clear cause, chills shaking the muscles, weakness spreading through the limbs. The immune system would respond aggressively, triggering inflammation and swelling in the lymph nodes. These swollen nodes, the buboes, are the biological signature of plague. Yet in its early evolutionary stages, the disease may not have moved with the same speed or ferocity seen centuries later. If flea-based transmission was not yet fully optimized, infection patterns could have been slower and less explosive. Some individuals might have survived. Others might have endured prolonged illness. Septicemic spread, when bacteria enter the bloodstream, may have occurred, but perhaps less frequently or less efficiently. Instead of a dramatic wave of mortality, early plague could have functioned as a recurring, smoldering presence within communities. Not a single catastrophic moment, but a pattern of periodic suffering. In small Bronze Age settlements, even modest mortality rates could have significant consequences. A village losing a handful of working-age adults would feel the strain immediately. Fields would go untilled. Harvests would shrink. Skilled craftspeople, metalworkers, builders, herders would disappear. If livestock were also affected through zoonotic transmission cycles, the impact would compound. Fewer animals meant less milk, less meat, less trade leverage. Disease does not only weaken bodies, it weakens systems. Yet when we turn to ancient texts, we do not find the word plague as we define it today. We find phrases like the wrath of the gods, or references to mysterious fevers sent as punishment. Illness was interpreted through cosmology, not microbiology. Without germ theory, societies explained epidemics through morality, divine anger, or supernatural imbalance. Anthropologically, this matters. It reminds us that disease shapes belief systems as much as it shapes demographics. The silence of the record does not equal the absence of disease. Bones rarely preserve the subtle signatures of infection unless mortality is extreme. Many pathogens leave no visible skeletal trace. Early plague, if present, may have moved through communities almost invisibly to us, felt intensely by those who lived it, but muted in the archaeological archive. History is often written in stone. Disease is written in cells. And cells decay. If we listen carefully, however, patterns emerge. Unexplained demographic dips, sudden abandonment of settlements, shifts in burial practices. These fragments do not prove a pandemic, but they invite epidemiological curiosity. In the human body, early plague may not have been theatrical. It may have been persistent. And in persistence lies power. The power to reshape communities quietly, generation after generation. Trade is rarely just about goods. It is about movement. Grain moving from field to warehouse. Animal hides crossing mountains. Ships cutting through salt water, their hulls heavy with cargo and unseen passengers. In the Bronze Age world, commerce stitched distant civilizations together. But every stitched network is also a biological corridor. Grain was power. Grain was wealth. And grain storage was a paradise for rodents. Where there is stored food, there are mice. Where there are mice, there are fleas. And where fleas thrive, bacteria find their vehicles. The earliest long-distance trade routes may have functioned as microbial highways, quiet, efficient, invisible. Ports amplified this system. Port cities were dense, humid, crowded. Sanitation was minimal. Food stocks were abundant. Ships arrived constantly, each one a floating ecosystem. Rats disembarked. Fleas followed. The bacterium did not need intention. It needed opportunity. Trade hubs, the pride of early globalization, may also have been the incubators of contagion. This is not a claim of certainty. It is an epidemiological possibility grounded in how pathogens behave in networked systems. When populations cluster and movement accelerates, microbes respond. They scale. What looks like prosperity at the macro level can conceal fragility at the microbial level. Perhaps the earliest phase of plague was not a sudden apocalypse, but a structural consequence of connectivity. Animals, humans, and trade, three forces converging, not by design, not by conspiracy, but by ecology. The microbial cost of progress may have begun far earlier than we imagine. History often speaks in numbers, percentages, population decline, agricultural output, trade contraction. But numbers do not mourn. A statistic does not sit beside a dying child. A demographic chart does not bury a husband at sunrise. Imagine a mother in a small Bronze Age settlement. Her child develops a fever. It lingers. The swelling does not subside. There is no diagnosis-only confusion, no microbial theory-only fear. She does not know the name Yersinia pestis. She knows only the silence that follows loss. Picture a shepherd watching his animals weaken. A few die, then more. The flock, once wealth and security, becomes uncertainty. Disease does not announce itself as zoonotic transmission. It appears as economic collapse on a personal scale, as hunger, as migration, as desperation. Now imagine a city once vibrant growing quieter. Workshops slow, markets thin out, fewer voices in the streets. No one calls it an epidemic in modern terms. They call it divine anger, a curse, a mysterious burning sickness. The language changes, but the human experience does not. Invisible microbes have always moved alongside us. The difference is not vulnerability, it is awareness. The unseen history of plague is not just about bacteria. It is about the continuity of human fragility and human resilience across thousands of years. For most of history, plague was a shadow in the records. Now, it is a sequence, a string of nucleotides extracted from bone, tooth, and time itself. Ancient DNA analysis has changed the rules of historical investigation. Scientists can recover fragments of Yersinia pestis from skeletons thousands of years old and reconstruct its genetic identity with astonishing precision. This is not guesswork. It is molecular archaeology. In laboratories across Europe and Central Asia, researchers isolate pathogen DNA from Bronze Age remains and compare it to modern strains. The result is a phylogenetic tree, a branching diagram that maps evolutionary relationships. Suddenly, what was once myth becomes measurable. Then there is the molecular clock. This method estimates when two genetic lineages diverged by measuring mutation rates, tiny, predictable changes that accumulate over generations. By calculating how fast Yersinia pestis mutates, scientists can estimate when it separated from its ancestor, Yersinia pseudotuberculosis. The clock does not tick in seconds. It ticks in mutations. Evolutionary modeling adds another layer. Researchers simulate how the bacterium adapted to fleas, how virulence factors emerged, how transmission efficiency increased. Early strains may have lacked key genes for flea blockage, the mechanism that allows efficient transmission through biting. That detail matters. It suggests early plague could have been slower, less explosive, but persistent. Science does not simply confirm old narratives. It reshapes them. With each genome sequenced, timelines shift. Assumptions are tested. Entire chapters of human history are revised. The past is not static. It is dynamic data waiting to be decoded. The most powerful idea here is this: microbes leave records. Not in stone inscriptions, not in royal archives, but in DNA. And with the right tools, we can read them. When we hear the words Black Death, we instinctively travel to medieval Europe, to collapsing cities, mass graves, and social transformation. Yet the pandemic of the 14th century was not the origin story. It was a climax. The bacterium behind it, Yersinia pestis, had already been moving through animal populations and human networks for millennia. Plague did not suddenly appear in the Middle Ages. It evolved. It adapted. It experimented. Long before chronicles described catastrophe, microbes were testing ecological pathways through rodents, through fleas, through trade routes. Civilization did not invent disease. It amplified it. As humanity expanded its reach domesticating animals, building ports, connecting continents, the microbial world expanded with it. Progress and vulnerability grew in parallel. Connectivity became strength. Connectivity became risk. The more complex our systems, the more efficient the pathways for invisible organisms. The lesson is not fear. It is awareness. We do not stand apart from the microbial world. We are embedded within it. Our history is biological as much as political, ecological as much as military. The rise of cities, the fall of empires, the restructuring of economies, all exist within a larger evolutionary theater. History is not only written by kings and wars, it is written by microbes. Plague did not vanish with the Middle Ages. It did not retire after reshaping Europe. Yersinia pestis still exists quietly within natural reservoirs across parts of Africa, Asia, and the Americas. Today, cases are rare compared to historical pandemics, but they are not zero. The bacterium survives in wild rodent populations, cycling silently between animals and fleas, waiting for ecological opportunity. The difference is not the microbe. The difference is us. In the late 19th century, during the third plague pandemic, the bacterium was finally identified by the Swiss-French physician Alexander Yersin in 1894. That discovery transformed plague from divine punishment into a defined biological adversary. Naming the organism was the first strategic victory. The 20th century introduced antibiotics, most notably streptomycin, followed by gentamicin, doxycycline, and ciprofloxacin. With early diagnosis and rapid treatment, bubonic plague today is highly survivable. Even pneumonic plague, once almost universally fatal, can be treated if caught quickly. Mortality is no longer destiny. It is a variable shaped by access to healthcare. Modern surveillance systems track outbreaks. Molecular diagnostics detect the bacterium within hours. Genomic sequencing monitors mutations in real time. Public health infrastructure isolates cases, treats contacts, and interrupts transmission chains. What once devastated continents can now be contained through coordinated response. And yet, the story is not closed. Antibiotic resistance is a theoretical risk. Climate change may shift rodent habitats. Expanding human-wildlife interfaces create new ecological friction points. The microbial world continues to evolve. So must we. The final message is not triumph. It is perspective. Plague reminds us that civilization is a biological experiment unfolding in real time. Our strength lies not in domination of nature, but in understanding it. The bacterium is still here. But so is science. If this journey into the deep history of microbes expanded your perspective, if it challenged the way you think about civilization, risk, and resilience, then you are exactly the kind of mind this channel is built for. Subscribe to become part of a community that explores history, not just through kings and wars, but through science, evolution, and the hidden systems shaping our world. Like this video so more curious thinkers can discover it. And share your thoughts in the comments, because the best insights emerge when knowledge becomes dialogue. In the next episode, we will continue tracing the unseen forces that shape humanity, where biology, history, and strategy intersect in ways most narratives overlook. Until then, stay curious, stay critical, and above all, stay healthy.